All right. Hi, everybody. I know in the last 5 minutes since I stopped recording the last thing and started recording now, there's been an overwhelming demand for you guys to be able to see me. I know we need that, personal connection and stuff. So here it is. I gave you a little thing down in the corner there. Hopefully I can show you guys how to do some work here. We'll see. This is going to be a learning process as we go, so just be patient with it. So here we go. It is just another day here in the Thunderdome while I'm recording. There's a load of laundry going. I think it's bath time. There was a pillow fort just built. The Descendants 3 soundtrack has been playing constantly all day. So it's just another day doing physics here. This is an old calendar, but it does at least have all of the dates of stuff here that, the topics that we want to work through. If you want to go ahead and get ahead, this calendar should be available to you. This is in OneNote, but you should have the same notes available to you inside of Teams. All right, now let's take a look at moving from translating to rotating, because that's the first thing we want to do. The biggest thing you can do here when you're trying to learn this stuff is you want to be able to go back and reference stuff. So my biggest piece of advice to you is read your textbook, read your textbook, read your textbook, read your textbook. I know that you might not have brought your textbook home, or maybe it's locked in your locker and that's currently locked down. But you can also get to your textbook from the Mastering Physics platform, and you should also have lecture slides that you can get to. If you can't get to the lecture slides, you can't find them under your resources, let me know and I will try to post them up myself. Now, looking at linear motion and going back through kinematics, we had position or displacement, we had velocity, and we had acceleration. So position was meters, velocity was meters per second, and acceleration was meters per second squared. And then we had all of our motion equations, so our constant velocity equation and our 3 kinematic equations. And then mass was listed as m, but was really basically an indicator of inertia. The more mass something has, the more inertia it has. We go over to rotational motion, and rotational motion has basically the same ancillaries, only instead of measuring in meters, we now measure in radians. All right, so instead of position, we measure angular position, which would be in radians, or angular velocity, which would be in radians per second, or angular acceleration, which is in radians per second squared. All right, and then all of your kinematic equations and your constant velocity equations still work. Only this time, instead of mass m, we have moment of inertia, which is a fancy term for rotating mass, and that is in uppercase I. We'll explain why this needs to be a little bit different than this soon enough, as soon as I get over here to moment of inertia. All right, so again, it's just kinematics. So what's my displacement? Just remember this has to be measured in radians. So you need to make sure that you take your calculator and move it over to radians when you're doing calculations for stuff that require sine, cosine kind of stuff. If they don't give it to you in degrees, they give it to you in radians. All right, so we'll hopefully work through a couple of problems like that. All right, so angular position, angular velocity, angular acceleration, and your angular motion equations, all very much the same. The only thing that's tricky here is that as you go through something that is rotating, everything that is rotating on the same object has the same angular velocity. Okay, so everything has the same angular velocity, angular acceleration, and angular position. So let's say I have an object like a stick. I'm going to draw a stick here, and I'm going to rotate it this way until it's to here. Can we see that? Yes, there it is. All right, so I've rotated it 90 degrees from top down. Okay, so as you rotate something 90 degrees like that, that is 1/4 of 2 pi radians. Yes, 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 yes. Okay, sure. And then as you rotate through something like that, the real trick is that you relate angular and linear stuff based on the radius. All right, so if everything rotates, let's say I have now lengthened that stick, right? All of the pieces of the stick here are traveling at the same angular velocity. But not all of the pieces of the stick are traveling at the same linear velocity. So in order for this piece of the stick to keep up with this piece of the stick, it has to travel faster and it has to travel a greater distance in the same amount of time. All right, and so you end up with the arc length equation. The arc length equation from your, hopefully, geometry or algebra 2 class, or who knows, new math. And basically what you end up with is that radius is the equalizer for everything. And so you can get back and forth between linear stuff and angular stuff as long as you take the radius into account. So we know that x is equal to r times theta. We know that v is equal to r times omega. And we know that acceleration a is equal to r times alpha, or angular acceleration. And so if you look at it, the units are going to be radians times meters, and radians per second times meters, and radians per second squared times meters. Like so. Get that closer where you can see. There you go. Okay. Okay. And you say, okay, well, that's great. I get meters per second, but there's still a radians in there. Well, don't tell your math teacher this, but radians are kind of like a phony baloney unit. They don't really count. And so you'll see a lot of old school textbooks. They won't even list the radian. So angular velocity isn't listed to them as radians per second. Angular velocity is listed as 1/seconds, which is the same as frequency. So you remember, where did you see omega, or what we called butt cheeks before? That was part of your oscillating equations, right? And so you had, let's say, x was a function of a cosine omega t, right? And period was related to that, so 2 pi over omega, and then frequency was even related to that because it was 1 over period. These things, yeah, there we go. Okay, those things, because they call it angular frequency, that's measured in hertz, which is 1/seconds. And so angular stuff, a lot of times, if you look at an old textbook, has no reference for radians at all. They just call it 1/seconds or 1/second squared for angular acceleration. So once you multiply the m in there, the radians just kind of goes away, and we get back to meters per second, or meters per second squared. Right. So as long as you have an object that is rotating without slipping, you can use these equations to get back and forth between linear displacement, linear velocity, linear acceleration, and angular position, angular velocity, and angular acceleration. Okay, moving things along, let's try a problem here. Let's see here. This one looks good. On a certain game show, contestants spin a wheel when it's their turn. I'm not going to say what game show it is. Okay, but one contestant gives a wheel a spin with an initial angular velocity of 5.4 radians per second. So that would be omega initial, which is 5.4 radians per second. And then it rotates. So its angular displacement, or theta, is 2.25 revolutions, and comes to rest on the bankrupt space. So we need to find the angular acceleration, and we need to find how long it took to come to rest. All right, so this is what we have. The problem is that we don't have everything in the same language. A revolution is not in radians, so we need to put that into radians. So you have 2.25 revolutions, and then we have to use some of that canceling some stuff out kind of stuff. So 2.25 and then revolutions. And we know that there are 2 pi radians per 1 revolution. You know, I really love the unit for rotations because you get to write rad a whole lot. Okay, and so then that gets us 4.5 pi radians because our revolutions now cancel out. Okay. So then that's how far we've displaced. Now there's some other information that we have there that we haven't taken into account. What is it? Well, we know our final angular velocity is 0 because it comes to rest. I know, this is my Dan Fullerton moment, isn't it? Like, okay, here we go. So we know that, right? And if we go back and we look at our equations, I have final and I have initial angular velocity and I have a displacement. So this one, right? That looks good. We should use it. Okay, let's do that. Okay, good talk. Now, so we know that omega squared is equal to omega squared final is equal to omega squared initial plus 2 alpha times theta, right? And so this is going to get me angular acceleration. And I can do this. All right, here we go. Okay, so I'm going to go grab my calculator and then we'll finish solving this part and move on. Okay, I'm back. What I did, I calculated out and I got that alpha is equal to negative 1.03, and that's in radians per second squared. All right, you might say, Smith, it's negative. That's not right, but it is because it's slowing down. All right, so it's okay, and we need to find time on that now. So let's take a look again here at our equations. To find time, well, I know initial and final angular velocity. I know acceleration now, so I can just use my first kinematic equation, and I can plug in that it's minus this over that, and I do a little bit of work here, and I get 5.4 divided by 0.03, is that right? Okay. 1.03, yes, no, yeah, no. That's also negative. So 5.4 divided by 1.0. And I get 5.24 seconds. Seems fair. Think so. And again, that is in seconds. Okay, so let's see where we are here. I have a minute and 20 seconds to get you through moment of inertia. Yeah, that's not happening. So we'll have to do it on a separate lesson, but that'll be a very short lesson. So let's then take a look at something else that might help us here. Is this the warm up? Okay, so a pulley is rotating counterclockwise direction. So this is another one to a mass suspended, blah, blah, blah. The mass causes the pulley's angular velocity to decrease. And one of the things I want to go over here is that remember that if something is moving in one direction and acceleration takes place in that same direction, then they are increasing speed. If acceleration goes in the opposite direction, then they have to be of the velocity, then they have to be decreasing speed. Okay, and then the last thing is, if an object is spinning in the counterclockwise direction, we always take that to be positive, just like we would say moving to the right is positive. All right, so you have to make sure that you're consistent with that. You don't always have to use that, but we just generally say that counterclockwise is positive and clockwise is negative. So this acceleration is negative because the mass is pulling downward which is pulling the pulley this way against its velocity.